So another property of liquids that we've sort of looked at before was something called vapor pressure. We've seen this briefly in looking at our behavior of gases in Chapter 5. To start out with, we're going to talk about the heat of vaporization. So a vapor is a gas phase of a substance that normally would be a solid or liquid at room temperature. Heat, we know, means enthalpy. So what we're talking about then is the enthalpy of vaporization, right? The amount of energy required to vaporize a mole of a particular liquid at 1 atmosphere. Evaporation, remember, is endothermic, so our delta H vaporization should have positive values. Okay? Water has a very large value for delta H vaporization, 40.7 kilojoules per mole. What would account for that? If you said IMFs, you're absolutely right. Water's intermolecular forces keep those molecules together. In order to vaporize them, you have to break all of those intermolecular forces. It takes quite a bit of energy. Initially, when you vaporize a liquid, if you're going to do this in a container, right? Initially, the volume of the liquid is going to go down a little bit as some of the liquid particles turn to gas. But eventually, you're going to reach a position called equilibrium, which means balance. Okay? And once you reach equilibrium, the volume of the liquid doesn't change. There's no more net change in volume. So the rate of condensation is equal to the rate of vaporization. So as many molecules as are leaving the liquid are returning to the liquid once you've reached equilibrium. So in picture A here on the left, we have a liquid, and some of the liquid particles are moving into the space above the liquid. They're becoming vapor. But eventually, for every molecule that leaves the liquid, you have to have return one from the vapor to the liquid, and that's what we call equilibrium at this point. But the molecules aren't static. This is dynamic equilibrium. Molecules are still changing phase. So the gas particles above are turning back into a liquid and vice versa. Okay? So initially, we look at this, the rate of evaporation versus time. We have a very constant rate of evaporations. The rate of condensation early on starts off very small. There's not much condensation until we reach equilibrium, at which point the rates will be equal. So vapor pressure is the pressure of the vapor phase of that liquid above the liquid at equilibrium. It's represented by P sub vap, okay, P vap. And you can use a simple barometer or manometer to measure it, but using a simple barometer, it's fairly simple to measure the vapor phase of a particular liquid, the vapor pressure of a particular liquid at equilibrium. You inject a little bit of liquid under the mercury in an inverted tube, and because mercury is so much more dense, the liquid that you inject goes right up to the top of the tube, and part of that liquid will evaporate and turn into a gas, and it'll push the mercury down a little bit. And then depending on how much it pushes the mercury down, that gives you an idea of its vapor pressure. Let's look at a little picture of what that might look like. So there's your basic equation. The atmospheric pressure is the pressure of the vapor plus the pressure of the mercury. So here we have, on the very left, we have just a simple barometer, a vacuum above it, no liquid, and the height of that mercury column is 760 torr. That's atmospheric pressure. If we then inject a little bit of water into that column, the water goes up to the top. Some of the water evaporates, forming water vapor, which pushes the mercury down a little bit. And so the height of the mercury now becomes 736. So the height of the water, the pressure of the water then is 760, the atmospheric pressure, minus the 736 that was left after the water evaporated, and that gives you 24 torr. If you use C2H5OH, that's ethanol. You put some ethanol in there. Ethanol turns into vapor, and it pushes the mercury down to a height of only 695, so its vapor pressure is 65 torr. And if we use something called diethyl ether, you get a tremendous amount of vapor pressure, 545 torr of vapor pressure. And it doesn't matter how much liquid you put in there, only a certain amount of it's going to evaporate, and then you're going to reach dynamic equilibrium at whatever temperature you happen to be at. And we're going to assume that we're at we're at room temperature here. So what accounts for the fact that water has a small vapor pressure at the same temperature? Ethanol has a higher one, and then look at diethyl ether, it's huge. What do you suppose accounts for that? Well, the short answer is intermolecular forces. The stronger the intermolecular force, the less of the liquid will evaporate at a particular temperature, and therefore the smaller the vapor pressure will be. We have a word for that. We call it volatile. So a volatile liquid is a liquid that has a high vapor pressure. Why does it have a high vapor pressure? Because it evaporates quickly. Well, why does it evaporate quickly? It has weak intermolecular forces. So there's a relationship. The stronger the IMF, the lower the vapor pressure. The larger the molar mass, the lower the vapor pressure. Why would molar mass have anything to do with this? Well, the short answer is that the bigger the molecule is, the more energy it takes to move around to turn it into a gas. So the bigger the molecule is, the fewer of those molecules will actually get out of the liquid, and you'll have less particles in the vapor, and you'll therefore have a lower vapor pressure. Now, vapor pressure is going to increase with temperature. As you increase the temperature, you give more molecules enough kinetic energy to escape the liquid, and therefore more particles will end up outside of the liquid in the gas phase. You can see this. This is just a table 10.8, where you have the vapor pressure of water as a function of temperature. As the temperature increases, the vapor pressure of water increases. Look what happens between 40 and 60 degrees. Between 40 and 60 degrees, the vapor pressure almost triples. So what's going on at that particular temperature? Well, at that point, you've reached the point at which you're breaking hydrogen bonds much more efficiently from 40 to 60 degrees Celsius. And from there, it goes up pretty steeply. You'll also notice if I were to graph this, that it's not a linear function. It's nonlinear, and that has to do with the interaction of molecules with each other. So you can see diethyl ether is a fairly steep curve. Ethanol is a little bit shallower, and water is even shallower than that, and that just speaks to the intermolecular forces that are involved there. So while that may not be linear, if you take the natural log of the vapor pressure and plot it versus 1 over T, you get a line. That's because the nature of this relationship is it's a logarithmic relationship. So if we look at the graph of vapor pressure versus temperature, it's nonlinear, but if we take the natural log of the vapor pressure, the y value, and 1 over the temperature in kelvins, we get a linear equation. And we can represent that if you realize that y now is natural log of the vapor pressure, and x is 1 over t. We can represent that with this equation. Natural log of vapor pressure is equal to now negative h vaporization over r times 1 over t plus c. So y equals mx plus v. C is the point at which it crosses the y-axis, not really important right now. But look at what the slope of this line is. The slope of this line is negative delta H vaporization over R. So it's proportional to the heat of vaporization. That gives you the slope of the line. The larger the heat of vaporization, the greater the slope. Well, the more negative the slope would be. This is called the Clausius-Clapeyron equation. Now, it's a little hard to solve for anything in this particular equation if you don't know what C is. However, if you know 2 points on the same line, you can combine this equation for 2 vapor pressures at 2 different temperatures, and you can get this version of the Clausius-Clapeyron equation. Natural log of vapor pressure at temperature 1 over vapor pressure at temperature 2 is equal to the same slope, delta H vaporization over R, times 1 over T2 minus 1 over T1. This form, by the way, is going to be very familiar, and you're going to see it several times in various situations. This kind of logarithmic relationship between variables and then sort of taking the log and 1 over another factor, you'll see this format very, very frequently in chemistry. So the Clausius-Clapeyron equation can be used to solve. There's 5 variables in there, and we can solve for any one of them given the other information. Usually we can use this to determine the vapor pressure of a liquid, and we'll do that in lab. Solids have vapor pressure as well as liquids do. Remember, the vapor pressure is just the pressure of the vapor of that substance above that substance. So solids that can sublime, for example, can produce a vapor. Solid going to gas directly. For example, carbon dioxide. Dry ice goes directly to carbon dioxide. It doesn't melt. That's why it's called dry. The heat of fusion, enthalpy of fusion, is the amount of heat required to do this. 1 mole of a substance to convert it from solid to gas, okay, or from solid to liquid. So dry ice will directly sublime. So does iodine. Solid iodine turns into iodine vapor instead of melting.